Today's presentation is Medical Imaging, More Science Than Art, presented by Mark Struthers. In the days of film screen imaging, radiologic technology was an art and a science. As we transition into the digital era, medical imaging is becoming more of a science than an art. With the growth of imaging technology, informatics, and information technology, the healthcare industry is in the midst of a transformative change. As medical imaging is a major part of patient diagnosis and overall outcomes, medical imaging is also changing rapidly. In the not-too-distant past, when a physician received an interpretation of a medical image, they only looked at the impression, unless there was something wrong, and then they read the text. Medical imaging reports today are much more informative and serve as a guide to the requesting physician. Today's requesting physician not only wants to know what the diagnosis is, they'd like information as to what to do. Radiologists, using deep learning and artificial intelligence, are able to answer their question. Today we'll explore modern technique and diagnosis to include informatics and artificial intelligence or deep learning. The one-time diagnosis with a radiograph has evolved, and today, over the last 120 years, we've developed a number of new imaging modalities, and with these new developments, we're able to provide more information for our patient diagnosis. Common types of imaging in the digital era include X-ray, CT scan, MRI, ultrasound, nuclear medicine imaging to include PET, positron emission tomography, and SPECT, single proton emission computed tomography. And in addition, we're able to do hybrid imaging, which we'll talk about in more detail in this presentation. Today, medical imaging results include 2D, 3D, and 4D images of anatomy and physiology. The focus of today's presentation is to compare the difference between medical imaging as an art and a science. There are two paramount differences between art and science. The first is that art is subjective while science is objective. The second is that art expresses knowledge most often in the form of a subjective representation, while science is the system of acquiring knowledge. Today's radiographers use sophisticated digital imaging modalities to acquire the information used to create the image. The acquisition of medical images is the foundation for diagnosis and treatment of pathology and disease. It is a radiographer's responsibility to acquire the best quality images for interpretation. The argument of science versus art in medicine is an ancient one and will probably continue as long as people practice medicine. Healthcare and medical imaging are complex activities which need many different types of professionals with different knowledge, skills, and competencies, and with specific roles in providing patient care. The rapid evolution of medical knowledge and medical technology has extended human vision into the very nature of disease. Medical imaging enables a new and more powerful generation of diagnosis and intervention. Using sophisticated modalities to acquire medical images, the radiographers and healthcare professionals of today provide much more information than the radiographers did in the past using film screen radiography. The original radiographs with film screen were interpretations of medical images that were subjective. With today's modern and sophisticated modalities, to interpret and to understand the depth of meaning or multiple meanings communicated in an image requires not only observation, but analysis. In film screen radiography, the interpretation was subjective. It depended strictly on the radiologist who is reading that particular exam. The quality of images in the past depended upon what the radiologist wanted to see and what the radiographer was able to produce. Today, we have more standardization because we have an all-encompassing imaging system with multiple modalities that have standardized protocols and procedures that are scientifically evidence-based. This means today's radiologist is interpreting images that are of higher quality and less variability. Using digital imaging and evidence-based diagnosis helps standardize medical image interpretation. Let's take a look at the medical imaging paradigm in today's healthcare environment. Medical images are the starting point for diagnosis of a variety of clinical situations. The clear advantages being their easy availability, relatively low cost, most are non-invasive, and their familiarity to medical professionals. The imaging techniques are relatively harmless, and fast imaging times make it more efficient. One of the dichotomies we find in this environment is that although we know everything is pretty much standardized, patients are inclined to think that they are unique. After all, no two people have the exact same genetic makeup or opinions or life experiences. So surely our medical problems must be unique as well, and therefore how can they be part of an informatics type of system? Well, we're not looking at their life experiences, which are unique, but we're looking at things that they have in common with other people. And we're looking at medical applications that are common to all people. Combining a huge medical database, we're able to access the information we need to better treat each patient. So let's put our medical hats aside for a side and take a look at data acquisition and distribution and what we have to work with in healthcare today. How much data do you think is available over the internet? That might be an overwhelming thought. Let's think about how much data is available in our hospital healthcare system. That too can be overwhelming. So let's think about how much medical imaging data we have in our hospital healthcare system. As you can see, we can go to smaller and smaller units to try to figure out how much data we have. But the overall data for all these units is known as big data. So our big dilemma is, how do we search this huge database to get the individual information we need for a specific examination in a specific patient? Now we can take analytics that has been used in business for a number of years and apply it to our database to help us create our images. Our first task is to define the parameters of what we're looking for. Once we have the parameters of what we're looking for, we can use machine learning to be able to get the data that we need to make a diagnosis. So the parameters of what we're looking for, we can put into data called supervised data. This gives our computer an idea of what to look for, and the computer now goes out onto the internet and any other type of information system is connected with to bring or extract that information to be looked at. All new data is brought in for extraction. This data is sorted and categorized, and the computer learns what type of information we're looking for, so in the future it only collects that specific information. That information is compared to our examination and we get a prediction. The prediction is an aid in diagnosis for the interpreting radiologist. We take the data that was acquired from the machine learning and apply it to deep learning algorithms. Deep learning algorithms are a way of sorting and interpreting the information. In other words, we're refining the data to be more specific to what we're looking for. This is done through neural networks. Neural networks are called neural networks because they're supposed to be modeled on how our brain works with synapses. As you know, synapses trigger function. So it is the function of the deep neural networks to look at all the input data for what we're trying to achieve. The computer then goes through and takes a look at this information and sorts it, such as shape, contour, intensity, all the different things that would be apropos to the image that we're trying to create. The recurrent neural network puts everything together and outputs the image with the data. Here we see a Venn diagram showing how machine learning, deep learning, and artificial intelligence all intersect. Artificial intelligence is simply taking all of the data that we have from machine learning and deep learning and put it into models which are more subjective, so it can suggest outcomes. As the data feed grows and the number of times we use this process grows, we become more accurate. And today, interpretation by computer is as accurate, and in some cases, or most cases actually, more accurate than comparing that to the readings of a radiologist. Using these tools, the radiologist takes the drudgery out of image analysis and is able to look at those things that are pertinent to diagnosing the image. The computer quickly provides the radiologist with the information that they need to make a decision. The computer does not replace the radiologist. It is a tool or an aid in making the radiologist more productive and efficient. The radiologist now has all the clinical information and comparisons to previous images that they need to make an interpretation and a diagnosis. Let's get back on track and look at art versus science in medical imaging. What happened to the art of medicine? The subjective practices of medicine in the past have mostly been replaced by the evidence-based medicine algorithm, which is the standard practice for physicians today. This means that many physicians who relied on experience and training can now supplement that experience and training by using the most up-to-date scientific research data that has already been analyzed and accepted as fact to augment their training. We're talking about art versus science, not exclusively art and exclusively science. So when we look at art, art is often seen as creative, intuitive, expressive, sensual, experimental, and emotional, while science is seen as methodical, logical, explicative, intellectual, cognitive, and rational. Logically, we use a combination of both of these to practice medicine. In the beginning, medicine was primarily an art. It was subjective. But as we got more information and more knowledge and refined our skills, it has become more scientific. In medical imaging, we must accept that things are different today and explore new options. The healthcare field must change some previous attitudes, and change comes about through understanding. So we need to have a deeper understanding of the benefits of informatics and digital to help us understand the benefits of digital in imaging. Let's begin by looking at the characteristics of Western medicine. We'll compare the art of medicine to evidence-based medicine. The art of medicine focuses on healing the person and the community with a focus on health. This is a subjective process, and complex diseases do not have a simple explanation, and outcomes are not always shown that are measurable. We'll compare that with evidence-based medicine. Evidence-based medicine focuses on pathology and curing disease. It is reductionist. Diseases are biological, and treatment should produce measurable outcomes. Intellect is primary. Medical practice is based on scientific theory. The physician is the authority, and evidence-based medicine fosters dependence on medication and technology, etc. It is the combination of the art of medicine and evidence-based medicine that comprises the characteristics of Western medicine. Western medicine differs from holistic medicine and Eastern medicine. Eastern medicine is focused on both the physical and the non-physical. In essence, the difference between East and West is that in the East, a holistic approach to medicine is taken, while in the West, a reductionist approach is taken. Let's take a close look at Western medicine, and we also have an animation that shows the optimized deep learning interpretation of medical images. Images and interpretations can be sent to a number of devices and can be read anywhere in the world utilizing the internet. Teleradiology is one of the foundations of telemedicine. Telemedicine allows us to share expertise and resources. Now that we've seen how deep learning is used in our workflow, let's take a look at the process itself. This animation gives an idea of what the deep learning process is and how it's used in interpretation. The amount of medical data doubles every 73 days. And each person has more than 1 million gigabytes of data collected during their lifetime. How do we take that data and create images in a cognitive healthcare organization? The first thing is we need a medical imaging big database. Using this database with deep learning, we can improve the productivity of the radiologist. Deep learning can search the database and find images that need interpretation immediately by the physician. Simultaneously, it can prepare information about the other exams in the queue. It will then send interpretation suggestions for the radiologist for these exams. Let's take a look at a Fuji workflow system as an example of using deep learning.
The advancements in diagnostic workflows. Riley starts immediately upon completion of an imaging exam. After instant recognition of the body part, Riley scans each organ for abnormalities. Upon abnormality detection, Riley triages studies and delivers a notification. The radiologist then immediately begins to interpret the study. Flexibility of the viewer can be automatically optimized for the type of exam and radiologist preference. Riley adds annotations and indexes to the suspicious regions to provide visual notification to the radiologist. Chart creation of measurements and findings are automatically created to track the size of the lesions over time. Semi-automatic report generation is supported based on the knowledge collected. Riley supports efficiencies for radiologists and clinicians during study interpretation by enhancing their diagnostic workflows.
Using film screen processing, an image is captured and a permanent display is created. With digital, we capture the data from the interactions of energy with tissue. We can store the data and we can reconstruct the data at multiple times and in multiple ways to create images. Although we can store the components of the digital image and reconstruct them in many ways, the components or the data that was collected during the interaction of the modality's energy with the patient's tissue only represents that particular acquisition at that point in time. The processing of the data or the latent image is dramatically different when we use film screen capture as compared to digital capture. In addition, the storage of the information from a film screen image and the storage of data from digital imaging is quite different. Storage, retrieval, and transfer of digital imaging or images is far superior to the traditional file room storage. In both scenarios, the identification of the images is paramount to retrieval. In both cases, the labeling and demographics must be accurate. Both the data stored and the film stored, or the exams stored, is important. We need to be able to retrieve the history of the patient. Physicians need access to this historical patient information, and we're able to transfer and communicate the information so that they can utilize it in future treatment of patients as well as comparison to new examinations. Most of us are familiar with the process of creating a film screen image, but let's take a look at the capture of a digital image and what we need to use for interpretation. When we use deep learning or artificial intelligence to be able to research an image and create suggestions for interpretation, there's a specific method that we use to create the search for the information we need. The first step in deep learning is to be able to recognize the shapes and areas of the image that we wish to interpret. This is done through segmentation. Remember, we are searching all of the image data for the patient that we have stored in big data. We only want to retrieve specific data for creating the interpretation. This takes millions of sorts and filters. Once we've acquired the data, we now use analytics to analyze the data. After the data is analyzed, suggestions are given to the radiologist for interpretation. The interpretation suggestions are more than just a comparison of past images in clinical history. All the patient's information, past and present, is utilized in comparing the new image to the previous image. This information is synthesized and analyzed to give the radiologist advice on interpretation. The truth is, most medical conditions have precedent. The right radiology test to order or the right medication to prescribe has a scientific basis, not an artistic one. And in the 21st century, that scientific basis can be defined and embedded into decision support tools for doctors. In viewing this image, we cannot deny the art, but we know that that art is based on science. As medical knowledge grows and medical technology evolves, we're basing more and more of our medical practice on science. The phrase, art of medicine, has been impacted as the rapid advancements of science in course of time has made the present-day practice of medicine more scientifically evidence-based. Most variations in imaging techniques and patient care are relics from the days before sophisticated information technologies and advanced diagnostic tools were available. The term art commonly refers to someone trying to acquire data or images without the tools that they need. The art is in the ability to acquire information without the optimal imaging modality, required knowledge, or skill set. With the training and the tools and the knowledge base that we have today, the practice of the radiographer has evolved to evidence-based scientific techniques. Today's radiographer practice their skills in many areas in healthcare and throughout the hospital. Radiographers are in contact with both inpatients and outpatients, a wide variety of healthcare professionals and ancillary staff, and many hospital departments. This requires a deep skill set and the ability to work with many types of healthcare patients and many types of healthcare professionals. In medical imaging, we must accept that things are different today and explore new options. The healthcare field must change some attitudes, and change comes about through understanding. We must understand how artificial intelligence, deep learning, and machine learning contribute to the tools that we utilize in creating medical images with multiple modalities. Digital images are created from data that can be reconstructed in many ways. Measurable digital imaging parameters have taken medical imaging beyond organ anatomy, pathology, into the realms of physiology, pharmacology, and cellular and molecular biology. Today's radiographer has to have a minimal amount of education about each one of these subjects. This knowledge, combined with the radiographer's expertise in medical imaging, creates optimal images. Although many of the tasks may be automated for the radiographer, their knowledge has to be all-encompassing. This being said, the technologists often abdicate too much responsibility to automated systems. The main goal of the radiographer is to acquire the optimal image and not just acquire an image. Despite the wide availability of high-end computing platforms and advanced color and grayscale monitors, the quality and properties of the final displayed medical image may be inadequate for diagnostic purposes. The clinical skills and knowledge base of the radiographer must evolve and keep pace with technology and changes in medical information. In dealing with digital or information data, there's an old saying about data: garbage in, garbage out. You cannot get a quality diagnosis if you do not have quality data. There are many ways a radiographer can err in acquiring the data for the image. Typical solutions to poor imaging technique errors is the individual wants to revert to luck or the art of imaging. What we really should be reverting to is science. This means very simply it's better to repeat an exam than to produce a non-diagnostic exam. In doing consulting work, I often found it very difficult when going out to try to solve problems at different facilities that the individuals actually having the problems have never read the operator's manual and do not fully understand the equipment that they are working with. This may be the result of the rapid evolution of technology and the inability to get quality training on the equipment and the upgrades in the equipment. Nevertheless, all vendors maintain information resources that you can utilize to find answers to your questions. For example, I just Googled this, GE Medical Training Resources. As you can see, there are resources available. You simply have to utilize them. Applications training is just the first step in understanding the use of the equipment that you have and the software that support it. Another avenue of training or communication for education is continuing education. This presentation is an example of the continuing education that is available for radiographers. The field of medical imaging is evolving rapidly, and the era of digital imaging is here. The skill set and knowledge base that once sufficed in film screen imaging is no longer applicable. In digital imaging, patient positioning and acquisition technique are paramount. Many of the variables in setting up the patient exam have been eliminated through automation. Automation and the elimination of many of the manual tasks or variables has allowed the radiographer to focus on patient care and acquiring the best possible image. In today's healthcare environment, medical imaging is not only creating information but communicating information. The imaging healthcare team in medical imaging, combined with all of the different modalities, has simply one purpose: to evaluate, analyze, and diagnose a patient's current status and communicate that status to healthcare providers for treatment. For human beings, there are three types of communication: written, visual, and spoken, all of which occur in the medical imaging process. A diagnostic medical image not only provides the visual representation of the patient's status, but it also has documentation embedded into the image for the referring physician to analyze. A dictated report accompanies the images. This report allows the diagnosis and suggestions for patient care to be analyzed by the physician. These diagnoses and suggestions are provided by the radiologist. Medical images and their accompanying reports can be transmitted in many ways to the referring physician. Actually, good communication stands out as the most legitimate aspect of the art of medicine as compared to the science of medicine. The most compelling aspect of medical imaging as the art of medicine involves communication. The application of medical science to the patient will always need a human component. How the radiographer communicates is a major portion of the perception of the quality of medical imaging that the patient receives when getting an exam. Radiographers must be proficient in the three basic types of communication with patients: oral, visual, and nonverbal. Quality communication is a major part in acquiring a quality examination. What many people think of as an art in medicine is the ability to make a diagnosis. Communication and information are part of making a diagnosis, and medical imaging is a primary component of patient diagnosis. In medical imaging, radiographers interact with the patient more than the radiologist. The four pillars of patient-centered care are improvement in public health, improved safety, improved efficiency, and, most importantly, improved patient satisfaction. Increasing specialization and fragmentation of healthcare, when more people are involved in a patient's care, there is more potential for miscommunication. We often spend minimal time with patients, but our impact makes a great difference upon the patient's perception of the quality of care they're getting and their satisfaction. Healthcare workers must understand that the patient's first impression of them and of their communication is extremely important. As technology gets more sophisticated, we're doing more exams and more complex exams than ever before. In medical imaging, individuals with multiple skills are required to work independently to achieve a favorable outcome. The current healthcare market demands higher proficiency, higher efficiency, and higher productivity for radiographers. These demands are premised on an increased patient load, increased number of technologies, more information, all of which seems to increase exponentially day by day. Radiographers interact with patients, and during this interaction, the patients often inform the radiographer of information that they had not given to the nurse or physician. Many times this information is pertinent to the patient's examination and should be communicated to the physician that requested the exam or the radiologist reading the exam. Radiographers have reported that the use of technology has increased the number of patients and the number of exams done daily. Without the addition of staff, what we find is that the interaction time and communication between patients and radiographers has not increased, but decreased. Patient interaction with the radiographer should be taken into account, and possibly staffing levels increased to get a better patient-centered focus on our examination. We need to balance productivity and efficiency with patient satisfaction. Today, one of the biggest problems facing physicians and clinicians in general is the overload of too much patient information and its availability. Let's look at and compare these two scenarios. The first, we do traditional film screen imaging. We take images, maybe 5 or 6, in an examination. They're sent to the radiologist where they're read, dictated, and then they are put into the patient's folder along with films after they've been transcribed. The film screen examination is then filed in the film file room. In this scenario, film screen, we have less images to be analyzed, less information that we can utilize, and our diagnosis is less complex. Therefore, the referring physician has less information for patient care. In scenario 2, we have a CT scan with thousands of images to analyze, a great deal of information to help in the diagnosis of those images, and the ability to communicate all kinds of information pulled from the hospital information system and electronic healthcare record to incorporate into our diagnosis, all the while giving the physician suggestions as to how they should proceed with patient care. In a simple exam-to-exam comparison, which scenario, 1 or 2, is more difficult for the radiologist and more time-consuming? How many patients actually go through our hospital system? Obviously, we're not going to image all of these patients, but how many patients do we image, and how many types of modalities do we have to image patients with? Obviously, you can see in today's digital era that there's an overwhelming amount of data that's available for both physicians and radiologists to examine. To be able to cope with this overload of information, we're relying more and more on artificial intelligence, machine learning, deep learning, and analytics. This graphic describes the terminology used in artificial intelligence and deep learning. It's obvious that artificial intelligence can tackle hundreds and millions of different types of tasks, all machine-oriented, and being able to integrate all kinds of data. But it is not good at making subjective decisions. The interpretation, which includes subjective material, is made by the radiologist. All the information is sifted by the artificial intelligence, bringing the radiologist those things that are pertinent to make a decision. This makes things more efficient and also the radiologist more productive. It would be impossible for the radiologist to go through all of the data in the big data volume and pick out those things that are clinically significant or actionable to make the interpretation. The segmentation and selection of data is done much quicker and more accurately with a computer system. As the computer sorts and resorts the information, we pare down the information to get the specific facts or data information that we need for our imaging exam. This information is then given to the radiologist, who makes an interpretation on this evidence-based scientific data. How do these processes and algorithms and all put together to make up the suggestions? What is machine learning? What is artificial intelligence? What is deep learning? Well, let's go through that a little bit. The first step in machine learning for software is to take in all of the data available in textbooks and care guidelines and then review examples of clinical cases. The process begins with the radiologist putting together a group of exams with a specific and known outcome. In machine learning, the computer takes all the information that it has gathered and compares it to this list of exams and the specific outcome that is being researched. It then creates processes or sorting processes to gather the specific information. These processes or protocols are known as algorithms. The more information the computer actually goes through and analyzes, the more refined and accurate the algorithm is and the information that it produces. All this sorting of data is transparent to the radiologist. All they see is the clinical decision support provided by the process. Artificial intelligence, or AI, is nothing more than a tool for the radiologist, and it provides clinical decision support. Artificial intelligence will not be diagnosing patients and replacing doctors. It will just make doctors more efficient. AI will be augmenting the doctor's ability to find the key relevant data that the doctor needs to care for a patient and present this data to the doctor in a concise and easily digestible format. AI will support medical interpretation. The benefits of a medical imaging test rely on both image and interpretation quality. The radiologist is responsible for the interpretation. Interpretation quality is prone to errors and can be limited since humans suffer from factors like fatigue and distraction. The variance in interpretation is one of the main reasons that we have peer review. Peer review is a mechanism where we can compare the interpretation and quality of interpretation. Artificial intelligence algorithms read medical images similar to radiologists. The algorithm and radiologists both identify patterns. Artificial software reading medical imaging studies can often match or in some cases outperform human radiologists. This is especially true for rare diseases. The artificial intelligence software has the advantage of reviewing hundreds or even thousands of these rare studies from archives to become more proficient at reading them and identify a proper diagnosis. Since these are rare cases, the radiologist may have never seen it before, or may have only seen one or two cases in their lifetime. IBM researchers estimate that medical images currently account for at least 90% of all medical data, making it the largest data source in the healthcare industry. Medical images are a big portion of the healthcare data in big data. Watson is an artificial intelligence data storage system that was created by IBM. In 2011, IBM created a new division, Watson for Healthcare. Let's see an example of Watson's capabilities. We'll start with a simple chest exam. Watson will begin by gathering all the information relevant to that particular patient's chest exam. Here we can see some of the pertinent information that Watson will gather for that chest exam. When the radiologist opens the study, all this information is presented in a concise format and greatly enhances the picture of this patient's health. Here we see a graphic of the applications that were suggested by radiologists when first asked about artificial intelligence as being a tool to help them in interpretation of images. We know today that these applications have been far exceeded utilizing artificial intelligence and the information that it can provide. Let's compare exam analysis by a radiologist using the traditional approach and then using the aid of artificial intelligence. In the traditional approach, the radiologist only has the information from experience and what he has in front of him to examine. Using artificial intelligence, the radiologist has the advantage of analytics. Analytics are extensively used to detect specific patterns identified with specific pathology. The imaging algorithms are capable of deriving metrics using intensive analysis of patterns in a given digital image and output scores that complement the analysis made by the radiologist. Here we have a good example of the process. Mammography is traditionally difficult to read because it's a soft tissue examination. In addition, there are numerous variables in mammograms based upon each patient having a unique breast composition. With traditional interpretation, the radiologist has to rely on their knowledge base and experience. Utilizing artificial intelligence, the radiologist now has all the information that is contained in the healthcare big data. The current exam is then compared with all the information that the big data holds on previous exams. Information is segmented, sorted, and then an analysis is made to give to the radiologist of the data. The analysis compares breast tissue and looks for anomalies to create suggestions for the radiologist. Using this additional information, the radiologist can make a more informed decision or interpretation based upon scientific evidenced data. The deep learning AI system analyzes medical images and then combines this insight with information from the patient's medical records to offer clinicians and radiologists support for decision making. Here we can take a look at some of the analysis that the deep learning does almost instantaneously, offering the radiologist some suggestions for interpretation. When we discuss deep learning, what we're talking about is the machine recognizing clinical problems in digital images ahead of the radiologist and providing solutions. Remember, these solutions are both patient and exam specific. Let's take an investigation of the overall process. The computer starts searching the raw data to segment out information that is germane to the examination, such as contour and shape. At the same time, the computer is examining intensities specific to different types of tissue. In addition to the image interpretation or analysis, the computer is also sorting the patient's medical and clinical history. The clinical data will help in the sort and also help in creating suggestions. The extracted information is stored in a voxel or a 3D volume of information. The computer can search this 3D volume by creating two-dimensional slices or traditional slices for specific information. Analyzing each of these slices in detail and then combining that with the algorithms that it used to extract and search for data, the computer then puts together a suggestion for the radiologist based on this evidence-based scientific information. For a human to manually duplicate this process would be overwhelming and daunting, but the computer accomplishes all of this in just a fraction of a second. This graphic displays the process done by IBM in its Watson healthcare system. Watson is a system that was designed to store universal healthcare data, access it rapidly, and analyze it rapidly. Watson has continuous input and continuous growth. This growth is fueled by the information provided by the software of vendors extracting information from the Watson system. They extract and input information, so the system continually builds. Watson analyzes the input data to maximize its output. The output data becomes more accurate as Watson increases the amount of input data that it analyzes. Medical images are acquired and read in medical imaging, but their use is universal throughout the hospital. Clinicians and healthcare professionals that are viewing medical images should have a good idea about how the images are created and displayed to enhance their ability to interpret for themselves the areas of interest. Clinicians and healthcare workers will post-process the images to get even better definition while they're treating the patient. A basic understanding of image manipulation and image display is critical to getting all the information that the images can provide. Medical images are used to communicate information about patient treatment and care, and we use several types of displays to view these images. The quality of the image display has a direct relationship to the image presentation. A wide variety of devices are used to display medical images throughout the hospital. The displays are designed to be utilized in the environment in which they are used, so there may be some differences in the quality of the image. Some displays are made for diagnosis and some are referential. Diagnostic monitors have the highest clarity and resolution to allow interpretation of the original image. Referential monitors are used by clinicians and healthcare professionals to review the images. Medical imaging is a technique and process of creating visual representations of the interior of a body for clinical analysis and medical intervention, as well as visual representation of the function of some organs or tissues. The quality of the monitor used depends upon the environment in which the images are being looked at. For example, the monitor used to acquire the images is of a lesser quality than the monitor that is used to diagnose the images. Whether we're treating a patient or diagnosing the patient, the quality of monitors is an important choice. It is important to understand image acquisition and monitor display, and we will review these topics now. We'll begin with terminology. The matrix is the area that the image is displayed in rows and columns of pixels. The word pixel is a contraction for picture element. Each pixel is a brightness representation or a color representation of the interaction of energy with tissue. The pixel is singular. It can only be one color or one shade of gray. Binary means two. In shades of gray, we start with 1 bit depth, 2 shades, black and white. When we talk about bit depth, we're talking about the range of the number of intensities that we can record at the one coordinate on the matrix or the pixel on the matrix. 2 to the 8th is 256. So when we record intensities that correspond to the image at this specific point, we have 256 intensities we can choose from. The combination of the pixel intensities create the image. The more intensities we can record, the more detail we can record. Changing from an 8-bit depth to a 12-bit depth increases the number of intensities from 256 to 4096 to choose from. When we're looking at these grayscale values, the total that we have to choose from is referred to as the dynamic range. We create the image by mapping the intensities that reflect the intensity that was acquired at a specific coordinate or place. That specific coordinate is the pixel. We map our image on a matrix. Let's build an image. Pixels are associated with 2 dimensions, height and width. We are 3-dimensional characters, and that's why we end up looking at the voxel. The voxel is height, width, and depth. The voxel represents the quantity of tissue that was interacted with. The amount and type of tissue are reflected in the intensity or the density of the voxel. All digital images are built with this concept or profile. Each modality creates interactions with tissue. Let's take a moment and see how a CT scanner utilizes this process. The image slice is obtained by a rotating X-ray tube capturing or interacting with tissue and collecting about 1,000 profiles per rotation. Each rotation is equal to a slice. A slice is a 2-dimensional picture of the tissue at a specific area. This area can be represented by a 2-dimensional histogram or bar graph of the intensities. The intensities are recorded, and then a number of them are sampled to create a single intensity or color or shade of gray in a pixel. This is called sampling. These samples are recorded as raw data. The samples are the raw data with very little contrast. When we look at an image, we look at it as contrast and spatial resolution. We map the raw data using a lookup table to change the contrast. Using the lookup table, we create the display image. There are 3 different steps in creating this display, and that's known as image processing. We acquire the raw data, and then we use pre-processing to correct or eliminate any artifacts that might have occurred during the acquisition. The corrected raw data now is applied to a lookup table for final image display. After acquiring the data, we use pre-processing, which is a low-level computer software application. The raw data that has been pre-processed is then put into software algorithms at a higher level in the computer to accomplish all of the different manipulations we need to create our image display. The final images are then stored in the computer. When a clinician looks at a display image, they are actually bringing up a copy of the original image. The clinician has to pull up the copy display and then manipulate the data in that display, creating a new set of images. The new images allow the clinician to answer or solve some of the questions that they may have about the patient's anatomy and physiology. Manipulating the copy data has no impact on the original data that was acquired at the modality. The acquisition data remains in its own file. Our ability to develop new ideas and adopt new digital technologies is highly dependent on our digital infrastructure. As digital image requirements change and evolve, we need to support the system with infrastructure that accommodates these changes. Infrastructure is everything from the environment, the HVAC, heating, ventilation, and air conditioning, to the data center infrastructure. We need to be able to support our existing technology as well as accommodate acquiring new technology. We've covered a lot of data, and I hope this answers our question: medical imaging, art, or science? This is Mark Struthers saying thank you for your time and attention, and we hope to be with you again soon.